Hey, Calculus! Rex here. Welcome back to Sequences and Series Make Sense, actually, the only series on YouTube where the framing of this whiteboard is as inconsistent as the rate that I make these videos. Today, we are going to be talking about the comparison tests, which is making scary stuff look simple. At this point in our series knowledge, we know how to deal with some simple series. We know how to deal with 1 over n. We can say, oh, I know what that is. That's a harmonic series. That diverges. Okay, and we know how to deal with 1 over n squared. You say, oh, that's a p series with p is greater than 1, and that converges. But what if we add a little bit of junk in there to like clog up our p series vision? What if we add in a little bit of gook? Like, what if we go 1 over 3n squared plus 5? And you say, oh, I don't know what to do with that. That's not a p series because there's all this gook here. And I know how to deal with n squared, but I don't know how to deal with 3n squared plus 5. That's different. And you're right. They are different series. They're going to have different sums. But we don't care about the sums. Most of this class doesn't care about the sums. What we care about is, does it have a sum? When you get super big, is this going to converge to a whole number? And you start thinking, well, when this gets super big, when this gets all the way up to infinity, how different is it actually from 1 over n squared? How different is it? Because we're not talking like plus or minus a couple. We're talking like orders of magnitude. When we're going all the way off to infinity, is this really any different? So let's think about this. When we're going off to infinity, if we've got like the infinitieth term in our series, like if we're going really far, this is going to be infinity squared times 3 plus 5. Now, would that really be that different if we ignored the plus 5? Is the difference between infinity and infinity plus 5 like enough to care about? No, because infinity plus 5 is still infinity. So we could basically like get rid of this plus 5 because it's a constant. And on the scale of infinity, constants don't matter that much. Then what about this coefficient, 3? Well, on the scale of infinity, 3 times infinity versus 1 times infinity, well, the 3 times infinity is a lot bigger. But they're still both infinity, right? We're thinking about orders of magnitude, right? The difference between a million and a billion is an order of magnitude, but the difference between a million and 3 million feels a lot smaller because it's on the same relative scale, right? Like these are basically going to do the same thing. So we can ignore that 3 coefficient. And so we can say, like in our heads, basically 1 over 3n squared plus 5, it's basically 1 over n squared. But that's not very mathy. Like that's not very, like, I don't know, it's not very precise mathematically. You can't go in a proof and say, well, these are basically the same thing. Because you have to prove it. You have to say why. And that's what the comparison tests are. The comparison tests are often like a big hurdle for kids in sequences and series because they involve these like funky limit equations, or they involve the first like equations that are a little bit complex that you just have to take for face value. But I'm telling you, you don't. All you're doing with these equations, all you're doing with these little theorems is saying, well, basically this equals that. Basically they're the same. And so how precisely we can do this? Well, we can do this directly. I've chosen an example where you know the relationship between these two, like term by term. You can say, well, these aren't just approximately the same, but every single term in 1 over 3n squared plus 5 has to be less than every single term in 1 over n squared. And why is that? Well, it's because, like when we plug in 1, this is going to be 1, this one's going to be 1, and this one's going to be 3 plus 5 is 8. And 1 over 8 is less than 1 over 1. And then that holds true for when we use n equals 2, because this is going to be 4, 12, 17. So this is going to be 1/17 when n is 2, and this is going to be 1/4, and 1/17 is less than 1/4. So we can say directly that every single term of these series, we can say 1 over 3n squared plus 5 is less than 1 over n squared. And this direct comparison, direct comparison test, this direct comparison tells us a ton, because we know what this does. We know that 1 over n squared converges. And so let's draw this out. Let me draw this out. If we've got 1 over n squared, let's get some colors going. Let's get a blue and a red. I missed the bag. I've got a bag of markers, and I missed the opening. Let's get 1 over n squared in blue. 1 over n squared, we know that it converges, so it looks a whole lot like this. It's this big swoop down that's going towards 0. And then we know that this is always less than 1 over n squared. It's always less than it. And let's think about this. If we're going back to like how we thought about it in the integral test, whether this converges or not is about the area under the curve, right? The sum of this sequence, the sum of this series, is like kind of analogous when we're thinking about it to the area under this curve. And so if we know that 1 over n squared, the blue dots, has a constant area under this curve, like it does converge, then there's like the area of 3n squared plus 5 has to be less than that. So of course it also has to converge, right? Because a real number and something that's less than a real number, something that's less than a real number also has to be a real number. Now, if 3n squared plus 5, if the thing that we knew what happened, like if this instead was 3n plus 5 and 1 over n, right, you can say the same comparison. You can say 1 over 3n plus 5 is less than 1 over n. But then we wouldn't know that this blue series converges. In fact, we'd know that the area under this, because 1 over n diverges, it's the harmonic series, this like goes off to infinity. And so something that goes off to infinity and something that's less than something that goes off into infinity, that doesn't really tell us anything about our series that we want to know about. And so that's kind of where the direct comparison test falters a little bit. It's super cool if like we've got our old example. I put the marker so far away. If we've got the old example of something that we want to know about, and whatever we've said it's basically equivalent to, like its simple counterpart, if its simple counterpart converges and is greater than the thing we want to know about, so this is thing we want to know about is a sub n, thing we already know about is b sub n. If a sub n is less than b sub n and b sub n converges, this is how you'll see it written, then a sub n converges, right? Or you could say the opposite, right? Like if a sub n is greater than b sub n, and we know that b sub n goes off to infinity, then yeah, a sub n also has to go off to infinity, because something that's bigger than infinity is really big. And b sub n diverges, then, so this, for this one it's a sub n converges, therefore a sub n diverges. And so in these two scenarios, if our funky series, we can just, first of all, we have to be able to establish this direct comparison between our funky series and our simple series. So we know that it's always less than, or it's always greater than. Then, if it meets these criteria, so like if it's less than a series that converges, it has to converge, because the AP Classroom guide talks about it like airplanes. Like if this one is coming in for a landing, and there's one that's under it, the one that's under it also has to come in for a landing, right? Like this little drawing. Or, in the other case, if a sub n is greater than b sub n, and b sub n is taken off, like b sub n is going up, diverging, then a sub n also has to diverge. So if it meets those criteria, direct comparison is simple, easy. You say, ooh, this is funky, I know it's basically this, I know that I can compare these two, and since I compare it, and funky is less than cool, and cool converges, then funky must also converge. That got a little complex, but I hope you can follow the ideas so that when you memorize the theorem, then it like cements a little better. It makes a little bit more sense. This is not where it stops, though, because you know how there were a lot of times when I was talking about that where I was like, well, this only works if. Because this only works if you can establish this direct less than, greater than comparison. That's why it's direct comparison test. And this only works if it fits these two criteria. But there's a way that's a little bit funkier that you can get around those criteria. This is called the limit comparison test, where what we just did was the direct comparison test. The limit comparison test doesn't care about establishing this direct comparison. It doesn't care about establishing those like two terms, like it doesn't have to be less than or greater than. It just cares about what does this basically do. Let's think about what a limit is for a second. If we have something that goes off to infinity, and we have something, well, let me start again. Let's say we've got some series that looks pretty scary. I don't know what to do with this. This is gonna like hide under my bed at night. That's terrifying. But we can use some of these some tools that we've learned before to make this basically on the scale of infinity much simpler. So as we thought about before, this constant doesn't freaking matter. We don't care about that. And then after we've established that this constant doesn't matter because of the scale of infinity, we're left with square root of n over n cubed. And, well, okay, we can rewrite the square root of n as n to the 1/2. And now you know how to deal with dividing dividing exponents. You just subtract. So n to the 1/2 divided by n cubed is the same as n to the 1/2 minus 3. 1/2 minus 3 is what, negative 5/2? And so this is basically n to the negative 5/2, which equals 1 over n to the 5 halves. And so we've just gone through the whole process that we went through before to make it simpler. This is the same process as we looked with at the beginning of the direct comparison test. But there's an issue. I need to uncross out that 4, because the 4 is, the 4 is still part of it. It's just not part of the simplification process. You can see how we got here. These are pretty much similar in terms of infinity. But we don't, at least I can't at first glance, tell you how they compare. I don't really know which one's greater or which one's less. But what I know is that their overall power, which is what we were doing here, we took the greatest terms, because those are the ones that will matter most as they go off to infinity, right? Even if there was an n squared term here in the bottom, if there was plus n squared plus 4, this n squared, I don't know, that's going to get pretty big. That seems pretty important. Well, as you get off to infinity, n cubed is infinity times more important than n squared, right? Because there's another infinity you've added in, you've multiplied by. So n squared even, when compared to this n cubed, gets so vastly smaller, gets so vastly unimportant, that we can basically ignore it, right? The n squared might as well be a constant, because it's so much, it's an order of magnitude less important than that n cubed. So what we've done is we've found the overall power of this funky looking fraction. We've taken the biggest thing on the top and divided it by the biggest thing on the bottom. And that's biggest thing in terms of exponential power. You understand. I'm sure you do. And so what we can call this as the basic power of this. I don't know. You don't need to call it anything, but understand that this has the same exponential power. This has the same order of magnitude as our original funky. I'm liking the word funky today. And maybe when I was doing that, you were reminded of something similar you've done before. Maybe you were reminded about taking the limit of things. Because let's take a trip back down pre-calc lane, where you learned things like, if we said the limit as n approaches infinity of n cubed plus n squared plus 4, the limit of our thing over here. In pre-calc, you probably learned the trick where when you're taking the limit as your variable goes to infinity, all you do is divide the first terms. So what we've done in doing this, in our quest to find something that is the same, basically has the same order of magnitude as you go off to infinity, is we've basically done the process of taking a limit. And so, how do we prove in a mathematical sense that this thing and this thing are the same? Well, we can compare their limits. Since we know that if you take the limit of this, you're basically ignoring everything and just caring about these first terms that we've taken out, the limits of these should be the same. And if the limit of them is the same, right, the terms basically become the same thing on the scale of infinity, then their convergence and divergence behavior should also be the same. Because it wouldn't make any sense if something that got really big was the same as something else that got really big, but the second thing didn't get really big. If they're the same, they have to do the same thing. And so by using limits, you can justify, rather than just saying, well, I did a little bit of thinky math and they're like the same thing, you can say, I did a little thinky math, found something that looks the same to me, and by taking their limits, I can prove that they have basically the same infinite trajectory. So what the limit convergent test actually says this is the stuff that they'll teach you in like the AP videos. They'll just start here without giving you any of the reasoning behind it or how to even use it. It's wild. It's wild. What the limit comparison test says is if the series are positive and they're both decreased, if the series are positive, so like you can't use any funky negative series or alternating series. We'll get to those later. If the series are positive, if the limit as n approaches infinity of some series a sub n over some series b sub n is, like, I don't know how to say, is a real number. Like, if it's not infinity, right, like if this converges to some, not converges, if this isn't infinity, if this is some whole number, then a sub n and b sub n do the same thing. And basically what we're saying here is we're taking the limit of each of these, because you know that, like algebraically, this is the same as taking the limit of the top and dividing it by the limit of the bottom. And all that division is like comparing orders of magnitude, right, at least on the scale of infinity. All this is saying is, do these have orders of magnitude that are similar, right? Because if something is like basically the same but double, right? Like if a sub n is twice as big as b sub n, they're still going to do basically the same thing, because twice a real number isn't going to be infinity. And so our limit is going to come out as 2. And so they're going to do the same thing. And so if we do this with, if we actually carry out the math, we've found the thing that we want to compare with, and now we're going to do the math, do the limit comparison test to prove that these are the same thing, or prove that they're like basically the same. We're going to say the limit as n goes to infinity, that was a funky infinity, of square root n over n cubed plus n squared plus 4. And instead of dividing, I'm going to multiply by the reciprocal because it looks easier. But you know that those are the same thing. Times n to the 5 halves over 1. Now sometimes these will be able to simplify out. And okay, whatever. I'll carry this out. N to the 5 halves times n to the 1 half. Remember that they're exponents. When you're multiplying exponents, you add them. So you're going to get that this is equal to the limit as n approaches infinity of 5 halves plus 1 half is 6 halves, which is 3. So you're going to get n cubed over n cubed plus n squared plus 4. And using the trick from pre-calc that I just talked about, the limit of the funky fraction is the same as just looking at the first terms, or like the biggest exponential terms, or the terms with the highest power. And n cubed over n cubed is 1. And so the limit, as this funky fraction thing goes to infinity, is 1. And gosh golly, 1 is a real number. 1 is not infinity. And therefore, I'm not going to write that out. Therefore, these two series do the same thing by the limit comparison test. And since they do the same thing, we know that 1 over n to the 5 halves is a p-series. 5 halves is greater than 1. And so this is a p-series with p is greater than 1, and therefore this converges. And by the limit comparison test that we just did, we know that these do the same thing, and therefore the sum from n equals 0 to infinity of square root n over n cubed plus n squared plus 4, which looked so ugly at the beginning, converges. And I think that's pretty cool. And you can do this with basically any series. Anything that looks like a funky polynomial, especially polynomials divided by polynomials, are really good for this, because all you have to do is take the power that it looks like it basically is, find that overall power of the series, and then say, do the limit comparison test comparing these two series. So the limit of a sub n divided by b sub n as n goes to infinity. Since you're doing this thing that ensures that they are the same thing, or basically the same thing, you are always going to get a whole number, or not a whole number, but like a non-infinity number as your result of this limit. And so that's just your way of proving that these are basically the same, and therefore they do the same thing. If you simplify this out and get an equation like this that diverges, and then do the limit comparison test and it's a whole number, then you know that the big funky one at the beginning diverges. And I think, like, I know that there's a lot of steps, but like these are all things that you know. Like, you know how to do this pre-calc stuff. Like, these are both of these things that I did are pre-calc stuff. It's just about putting them in this new calculus-y, like, frame of mind, putting them in a calculus-y context. A, it makes sense why we do these things in pre-calculus, because you need them in calculus. And B, it also shows you that, like, the limit comparison test, once you look past its rules and its weird, like, limit of dividing two series, like, that's a lot. Once you look past all of the funky stuff, just like we did here, you can simplify it down into something that you can understand. The limit comparison test makes sense, actually.